Hi guys, it's your guy Olumide, and today we'll be solving another one of the most commonly asked tech interview question: find all permutations. It's a DSA problem that's commonly asked by top tech companies including Google, Amazon, Netflix, Meta, Microsoft, Apple, and other top tech companies. The problem statements state that return all possible permutations of a given array of unique integers. They can be returned in any order. And we are given this example input nums, right? So this example input nums is an array of integers 4, 5, 6, and this is the output here, which is actually the permutation in different orders. So just like mathematically you can calculate the permutation of this array of nums because it has a length of 3, right? So 3 permutations is gonna give us 3 times 2 times 1, which is 6. So that's why the total number of possible permutations of this array is 6. In solving this problem, let's figure out how to build just one permutation. So let's consider the array this nums array 4, 5, 6. Let's see how we can build just a single permutation out of this array of nums. First of all, we are gonna pick the first number in the array. We are gonna pick it and we are gonna add it to our use. Why? Because we'll be needing a data storage to store used numbers, right? Because permutation can contain each unique number in the array in different order, right? But it must not contain the same set of number. Like it must not contain 4, 4, 5, 5, or 6, 6. It must be unique in different order. So by choosing 4 now, we are then gonna choose the second number in the array. So and this time we're gonna choose 5, right? So and now our array is now made up of 4 and 5, since we have chosen 4 and 5, and then we just continue to choose on and on till we get to the same length, till we get a combination that is the same length of the array. So meaning that we just have to choose again where we are gonna choose 6, which is the last number in this particular example, whereby the length of the array is just 3, right? So I'm gonna choose 6, and now the used we're also going to keep track of each used number using the hash set, and that's how simply we found one permutation. Now that we found a permutation, let's backtrack to find the rest, and then we backtrack by removing 6, which is actually the last number that we added into the list. So we remove 6. So removing 6 now, we are left with 4, 5. This list 4, 5. Now we ask ourselves, what other number in the nums of array that is given to us, this particular nums of array here, what other number here can we add to make a new set of permutation or a new permutation? Fine, there is no other number, because in the nums of array that is given to us we only have 4, 5, and 6, and since we have already gotten one permutation 4, 5, and 6, and then we backtrack by removing 6, there's no other number that we can add to create a new permutation, right? So because 4 and 5 is the candidate that we have here, 4 and 5 is the, after removing 6 we have 4 and 5, and there's no other number we can add, right? Except if we want to add the same set of number, so which we don't want to. So what we do again is that we backtrack one more time so that we can just have 4 remaining in our array. So now that we have 4 remaining, so we now ask ourselves, right? So we will backtrack by removing we backtrack again by removing 5, right? So we have 4. Now that we have 4, we ask ourselves, what can we add into the array that's gonna give us a new set of permutation? So and then we see that we can add 6 now, right, into the array, so as to make up 4, 6. So don't forget, permutation is just the same set of number arranged in different orders. So all possible permutation, all possible orders that we can place norms, right? That's what we call permutation. So now that we added 4 and 6 now, so we added 6 into the set, or let me say into the we used to call it candidates. So its candidate is any number that can possibly give us a permutation, a possible permutation. So now we have a 4 and 6, and now that we have 4 and 6, we now see that by choosing 5, we can actually add by choosing 5, we can come up with a new permutation, which is 4, 6 and 5, right? So, and now we found another permutation. So, and that's how we just keep moving forward and backtracking until we get the whole permutation. So that's just what I just explained, one single part right here now. So whereby we move from 4 to 4 and 5 to 4 and 5 and 6, and then we backtrack to 4 back to 4, right, to create 4 and 6, and then 4, 6 and 5. So similar thing, after finding out 4, 6 and 5, we backtrack again to 4 and 6, because there's no other thing to add other than 5, which have been added actually. We backtrack again to 4, right? And at this point of backtracking to 4, so we have removed 6, right? So we see that since we have already touched 4 and 5, and we have already touched 4 and 6, meaning that we have touched 4, 5, 6 and 4, 6, 5, then we just need to backtrack again to the beginning, right, where we have empty array, and from there we choose a new value 5. So choosing 5 now, we can then proceed to add 4 to our 5, and then to add 6 to it, and then after creating this new permutation, we backtrack again to this 4, 5 and 4, but you know there's nothing to add again aside from 6 at this point, because there's already 4, there's already 5, and now it's 6. So, and because we have used 6, what we do again is that we have to backtrack again one step to the back, so that we can create a new permutation. So at this point 5, we see that we have not added 6, like we do not have this order 5, 6. So we create this order 5, 6, and then after creating it, we now can add 4 again to it. So, and same thing apply here, whereby after creating permutation 5, 4, 6 and 5, 6, 4, there's no permutation we can create starting from 5. Why? Because we've touched 6 and then touched 4, and we've touched 4 first and touched 6. So that's the two permutations that can come out of this particular range here. So we backtrack again to the beginning, and we use 6, right? And by using 6, so we tap into 6, 4, so, and then we tap into 6, 4, 5. So since there's no other value to add, we backtrack again to 6, 4, and similarly there's no other value to add. Why? Because we've actually 5 is only the only value we can include to 6, 4, and that has been included there. So we backtrack again to this point whereby we create 6, 5 instead. So and that leads us to 6, 5 and 4. And that way we have efficiently create all possible permutations. Now, to generate all these possible permutations, we have to be able to efficiently traverse this space tree. So by efficiently traversing this space tree, we will be able to generate these permutations. And then this is the step to actually traverse the space tree. First is that we pick an unused number and add it to the current permutation candidate. These are what we call permutation candidates. Any of these half completed lists are actually a candidate. Why? Because one way or the other they're gonna result in the eventual possible permutations, right? So we are gonna pick the first things to pick an unused number and add it to the current permutation candidates, right? So just like what we did right here. So right now at the beginning is just an empty list. Our candidate is just an empty list, and then because 4 have not been used, we add it to the list, right? And adding it, we are gonna add it to the used as well. So that's what it's trying to say, that we have to mark this number as used by adding it to the used hash set. And why we mark it is because we don't want to use it again for that same particular candidate. We don't want to be having multiple numbers or the same number twice in a candidate, right? So now the next thing then is to make a recursive call with this updated permutation candidate to explore its branches. So what that means is that, okay, you see, after adding 4 to the candidates, right? You said that we use a DFS. We are going to be using a DFS to explore the branches, and what it means is that right from this point now, you will see that we consider two branch, the one whereby we have 4,5, and then one whereby we have 4,6. Why? Because 5 and aside from 4, 5 and 6 are other branches, or let me say other numbers in the array that we have not used, with 4, right? We have used 4, and then we have to traverse and explore the branches that branch from 4. So because the array is actually an array of 4, 5 and 6, right? So having used 4, from 4 we are going to traverse and find all possible combinations that we can get from this branch, from 5 and 6. And that's what happened there, whereby we choose 4,5 that later extends to 456, and then we choose 4,6 that extends to 465. So that means we call a DFS. We're going to be calling a DFS on this particular candidate after adding 4, right? We're going to call a DFS on it to explore the branches, and then after that we're going to backtrack by removing the last number we added to the current candidates array, and we remove it also from the used hash set. So what that means is that after exploring this part, right, look at this part, after exploring to get 4,5, and because we added a new value 5 into the candidate, right, we have to explore all possible part again right from 5, which is just 6, because we've added 4, we've added 5, just 6 remaining. So after exploring the parts to provide 4, 5, 6, we see that we backtrack. Why? Because we need to explore other possible branches, but because we have actually added 4 and 5, and then we've come here to add 6 as well, there's nothing we can actually add to this particular set of number here, I mean 4,5. So that's why we backtrack again to meet 4, and at this point there are still things we can add, which is 6, right? So, and that's what we do add 6, and then after adding 6 we take this part again, we explore possible value that have not been added. You see inside our use is 4,6, so 5 is not yet there, so we try to explore this particular part to give us 4, 6 and 5. So, and don't forget that as we are backtracking, we are actually removing the last elements from the candidate, right? We are popping out of that last element, and we're also removing it from the used, so that we can be able to explore other branches. So these are the 3 steps. So whenever a permutation candidate reaches the length of n, we add it to our output. So what this place means is that, imagine when at this point whereby we try to add a new number into the candidate, and we try to explore the branches, right? So exploring the branches, we add another new number, and we try to explore the branch again for this particular one, and now that we come across 4,5, 6, which is actually a candidate that have the same length as the input array norms, definitely that tells us that we have actually created a permutation, because a permutation must be of the same length in any order, the same length as the original array, but in any order. So for us to create something like this that is of the same length, definitely we have created a new permutation. So what we do is that we actually add it to our output array. So that's how we get to know that we have reached a leaf node. That's what tells us that we have reached a leaf node like this. So at that point we add it and we backtrack, right? So that's how we go about solving this problem. So let's go into the code implementation for a more better understanding. Let's go into the code implementation for the find all subsets DSA problem. So we have the find all subset, so as our function name. Now we're going to be collecting an argument norms, so which is the list of the array of numbers that we want to extract all possible subsets from. So it's going to be a list of integer, right? So, and the return is going to be a list of integers. Why? Because we are returning all possible subsets. So now we are going to be defining a res, which is the output array. So results, it stands for results. So, and it's going to help us to collate all possible, we're going to be appending all possible subsets into it. As we are finding this subset, we're going to be appending it into the res array. So now let's call the DFS. I'm going to call the function DFS, and what it does is that it helps us to iterate and backtrack to find all possible subsets. Now we are going to be passing in 0 into it, and this represents the row and the index, so it represents the current index, right? So don't forget, we'll be doing it at each index. We're going to be making a decision of whether to include it or to exclude it. So it represents the index. So this list actually represents the subset. Why? Because as we are actually, we'll be appending elements into the subset, right? So as to create all possible subsets, and then we'll be passing our nums and the rest. So now let's define the function DFS. So I'm going to collect that index as I, which is going to be an integer. We are going to collect this as subsets. So the list as subsets, which is actually a list of integers, right? So I'm going to be collecting nums as a list of integers as well, and we'll be collecting res as a list of integers, and then the return is going to be none, right? Because really all we are just gonna do here instead is that we are gonna return res. So hoping that res is gonna, at the end of by the time we call this function, res is gonna contain all possible subsets, right? So we don't need to return anything from this DFS function, because it's just going to traverse the subtree. That's what it does. So now let's place the edge case, or let me say the best case, whereby we'll be returning. So whenever I become equals to the len of nums, so according to logic we explained, at that point it actually contains our subset, the leaf node. If you go back to the logic, right, you find out that at the point whereby I become equals to len of nums, so we consider, let me put down this is the example we are given in the problem statement. So when I move from 0, it's index. So when you move from index 0 to index 1 and then index 2, and then it moves to index 3, which actually is equals to the len of nums, definitely it contains that particular, we just have to append that particular subset into our res outputs. So that's what it means, and by then we can simply return. So that's in a case whereby I equals to 3, right? So for this particular example here. So otherwise, what we want to do is that we want to add to our subset dot append the nums of I, the element at that particular index. We want to append it. So nums of I, and after that we call DFS so that we can traverse deeper, and this time we are going to be passing in I plus 1, because now we want to add, we are performing two conditions here, or let me say two condition or decisions, whether to include or not to include the current elements into our subset. So at this point we are including it. So similarly we are going to exclude it. So those two we are going to be performed, and the 2 is going to lead us to all possible subsets, just like you read you saw in the code in the logic. So at this point I added the particular elements, the current element, into the subset, and then I called DFS to traverse deeper into the tree. So similarly I'll be removing it from the subset dot pop. So this way we remove it from the tree, and at the same time, so this is the second decision, right? The second choice of excluding it. So this time what we appended at first, I pop it out, thereby I did not include it. and then similarly I'm gonna call DFS on it. So, and this is how we essentially solve this problem. So this way now is gonna include it and then traverse into the tree, and similarly after doing that it's gonna remove it, that is not including it, and traverse into the tree. So at each case it's gonna be adding 1 to the current index so that it could make that same decision for the next element in the nums array. So let's run this function and see how it goes. Fine. By running it, we see that it gives us this all possible subsets, which you can see here: 4, 5, 6, 4, 5, 4, 6, 4, 5, 6, 6, and empty, right? This is it right here. So, and these are all possible subsets that we can extract from this input array 4, 5, 6. So this is how to solve this problem efficiently, and I hope you do understand. If you do, kindly subscribe to my YouTube channel and like, comment and share. Thanks.